Hi everyone, I'm here in Chapter 6 of the course packet, which is about multiple regression, and the goal of this video is to teach you one basic idea that will run throughout much of the rest of the course packet. That is the idea of a partial relationship between a predictor and a response in a multiple regression model. So to motivate this idea, I'm actually going to look at the picture on the next page, and what you're seeing here is a three-dimensional plot projected onto the 2D page of three variables. So every single dot in this picture is a car, and you're seeing three facts about that car plotted. Along the vertical axis, you're seeing the gas mileage of that car, specifically the highway miles per gallon, 15 per miles per gallon up to 25 right here. Along this kind of left to right axis, you are seeing the engine displacement of the car. That's a measure of how big the engine is. If you've ever seen a car engine, it has these little cylinders in it where a piston kind of sits in that cylinder and it moves up and down in order to make the engine turn. And what the engine displacement represents the cumulative volume of all the engine cylinders. Okay, so you know, like a 4-cylinder, a V6, a V8, etc. That's this axis right here. And then on the axis kind of going back into the page, you're seeing the weight of the car in pounds, 3,000, 4,000, 5,000, etc. And you can see a very clear relationship among the three variables in this particular data set. It's a little bit easier to see in this picture down here, which shows a regression plane fit to this data. And you know, because it's difficult to sort of see in 3 dimensions on a 2-dimensional page, we've added the colors of the dots here. And so this color scale on the right-hand side here also allows you to kind of pick out how high the dots are up on this vertical axis right here. So the very, very dark red represents the dots that are high, and the very dark blue represents the dots that have low gas mileage. So this is our first example of a multiple regression model. And it helps to go back to the first page and ask, what is the equation for this model right here? And it turns out to be this. This is a multiple linear regression model where there are two partial slopes. Beta 1 right here is the coefficient in the engine displacement direction, moving left to right. Beta 2 is the coefficient on the weight variable, moving foreground to background in that 3-dimensional picture. And then y, obviously, is the gas mileage. That's the response variable. Since the fitted plane, and this equation right here, let me erase this part right here and point out this equation right here, not counting the residual, that's the regression plane right there. So before we had a line, and now we've got in multiple dimensions a regression plane. And then obviously, as always in a regression model, we have the residual as well representing the misses of the model. Okay, so let's take a look at this again, and you can get a sense of the plane, the sort of orientation of the plane in this dimension right here. Represents the x1 coefficient. The tilt of the plane in this dimension right here represents the x2 coefficient, and then the errors, the distances from an individual dot to the plane itself represent the residuals. So that's a multiple regression model in a nutshell, and we can fit that by least squares in a very, very straightforward way. And in fact, it helps to kind of go point by point here and ask ourselves, what changes and what stays the same when we go from 1-variable regression to 2-variable regression? Obviously, you're getting a sense of, of one thing that changes, which is we move from 2-dimensional plots, you know, 1y and 1x, to multiple dimensional plots, more than 1x versus 1y, and in this case we've got 3 dimensions. But actually first I think it helps to think about what stays the same. Okay, you know, I'll just point out, you know, that even though we've talked about 2 dimensions right here, we can easily fit more than 1 variable. Okay, and that there would be a p-dimensional plane right here for p different variables. That is a very, very difficult object to visualize for people because we can naturally think in 2 and 3 dimensions. And so, you know, it just becomes impossible to visualize this thing. We've got more than 2 predictor variables. but there's no problem describing it mathematically using an equation like this. Okay, so we will kind of rapidly move from 1 to 2 to more than 2 variables. We'll have trouble visualizing it, but no trouble describing it using an algebraic equation of a p-dimensional plane. Okay, so what actually stays the same when we move from multiple regression, from single variable regression to multiple variable regression? Well, the first thing that stays the same is that we still fit the variable using least squares, okay? So we still use OLS, ordinary least squares, to fit the variables, okay? And that gives us fitted values, y hat I right here, and our goal is, if you think about summing up the errors, the differences between the actual y variables and the fitted y variables described by this equation up here, you get the sum of squared errors, and the principle of least squares says that we should choose these parameters, beta naught hat, beta 1 hat, all the way up to beta p hat, the coefficient on the pth variable, in order to make this quantity, the sum of squared errors, as small as possible. That's exactly the same as in one variable regression, and again, just as in one variable regression, most statistical software will make the calculational tedium of this fitting by least squares simply a non-issue. You just type in one line and out pops the fitted parameters, beta naught hat, beta 1 hat, beta 2 hat, etc. So that stays the same. Another thing that stays the same is the interpretation of the residuals. So the residuals still have the interpretation that they are the part of y that is unexplained or unpredicted by the variables in the model, on the right-hand side of the model, the p different x variables. Okay, so we can still interpret this residual, ei equals yi minus y hat I, as the outcome variable adjusted for all of the systematic effects in the x variables, except now there's more than one of them. So we were statistically adjusting for more than one thing at once. A third thing that stays the same is that we still use r squared. So r squared still summarizes the fit of the regression model, and it still has exactly the same interpretation that it did before. It's the ratio of predictable variation to total variation, and those quantities are defined in exactly the same way as they were before. Here's the predictable variation. The sum of this right here in the numerator is actually the unpredictable variation, and then down in the numerator we have the total variation. The only difference is that y hat is now a function of more than just one variable. It's a function of multiple variables. But the interpretation of r squared as the total fraction of predictable variation in the data set stays exactly the same. Final thing that stays the same, or at least final major thing, is that we still estimate the residual standard deviation using the same formula. Here's the total, the unpredictable variation, and you can think of that as like the numerator, and then we divide that by the residual degrees of freedom. So the residual degrees of freedom, DOF, is n minus p, the number of data points minus the number of free parameters in the model, right there. Okay, and so and I'll write that again since I slightly messed it up. N minus p is the residual degrees of freedom. N is the number of data points, p is the number of free parameters, and only one tricky thing to keep in mind is that for a model with, say, 2 variables, like our model of gas mileage versus engine size and weight before, we have p equals 3 in that context because there's an intercept, beta naught, and then 2 coefficients, beta 1 for the engine size and beta 2 for the weight. The nice part is that your regression software should pretty much keep track of that for you. All right, so that's what stays the same. Now let's ask ourselves what changes when we move from a single variable regression model to a multiple variable regression model. And the most important thing that changes is the interpretation of each beta coefficient. And let's focus on that equation to understand exactly what's going on. So here is our example of a 2-variable regression equation right here. Okay, so let's be concrete. X1 was engine size from our previous example, and X2 was weight. Okay, and we're saying that the outcome, gas mileage, depends on both engine size and weight. And so you kind of have this additive decomposition of these two effects. The gas mileage is some baseline, an intercept, plus an effect due to engine size, and then an effect due to weight, and we sum the two effects together to get the joint effect on the response variable. Now, if you want to think about, let's say, interpreting this particular coefficient right here, let's say the beta 2 coefficient in this regression equation, let's isolate that part of the equation on the right-hand side. And the way we do that is by simply subtracting this part, the effect of x1, and moving it over onto the left-hand side of the equation. Okay, so what we've got here now, if we do that, is on the left-hand side, y minus the x effect. On the right-hand side, we have a regression on x2. And so both of these pieces are familiar. On the left-hand side, what do we have if we take a y variable and we subtract an effect due to an x variable? Well, we have the y variable adjusted for the effect of that x. It's sort of like a partial residual, accounting for one of the two effects in this regression model. So that's on the left-hand side. Now what about the right-hand side? Well, on the right-hand side, again, you're used to thinking in these terms. This is simply a one-variable regression over here on x2 plus a residual. So on the left-hand side, we have y adjusted for x1, and on the right-hand side, we have a regression for x2, and putting those two pieces together leads to a powerful conclusion. It tells us that beta 2, the regression coefficient in this equation, is the relationship between y and x2, in this case the weight variable, once we adjust for engine size. Or said another way, beta 2 is the coefficient on x2 holding weight constant. The coefficient on engine size holding weight constant. Okay? And that is crucial. That tells us that beta 2 in this context is a partial slope. Okay, so on the left-hand side, we've got a partial residual, y adjusted for the engine size effect. And that means on the right-hand side, we have a partial slope. Y adjusted for engine size is a regression on weight, and the coefficient on that weight is x2. So again, putting all of these pieces together, it's non-trivial, but if you put them all together, what you find is that the coefficient in a multiple regression model is a partial relationship. Beta 2 right here represents the rate of change of, just to be very concrete here, what is y? Y is miles per gallon. So beta 2 represents the change in miles per gallon when you change weight by 1 unit, 1 pound here, comma, holding engine size constant. And that extra little clause there, that extra holding engine size constant, is something fundamentally different from what we have when we have a one-variable regression model where there's no notion of adjustment, there's no notion of a partial residual or a partial slope. It's simply an overall relationship. So this gets us, and of course the same line of reasoning would work in reverse for x1. If we instead now come here and we think about isolating the x1 effect on the right-hand side, well, that means we've got a partial residual over here on the left-hand side, highway miles per gallon adjusting for weight, and on the right-hand side we've got a regression on engine size. Okay, so that tells us that beta 1 is a partial slope, a partial relationship between weight as the y variable and engine size as the x variable, holding, let me back up there, it's the relationship between miles per gallon as the y variable and engine size as the x variable, holding weight constant. That means it's a partial relationship holding the other variable constant. Okay, so that, it helps to think about partial relationships in the context of a multiple regression model, thinking a little bit visually here. So I'm going over to page 133. What you're seeing here is now the original overall relationships between mileage and engine displacement here on the left and mileage and vehicle weight here on the right. Okay, and the slopes of these lines right here are denoted in the equations. Let's focus on this plot on the left-hand side first. This is the overall relationship between mileage and engine displacement, and you can see this has a slope of minus 2.5. And by overall relationship, I just mean, hey, we plot highway miles per gallon on the y-axis versus engine on the x-axis, and we ask, what's the slope? Just as we learned to do a while back. and that slope is minus 2.5. The interpretation of that is when we change engine size by 1 unit, in this case 1 liter of displacement, that's the unit of engine displacement, we change highway miles per gallon on average by minus 2.5. So 1 extra liter loses you 2.5 miles per gallon of highway gas mileage. All right, so that's an overall relationship right there, or an overall slope. Similarly, on the right-hand side of this plot, we've got an overall slope between weight as an x variable and mileage as a y variable. And again, overall here, because we're just plotting mileage versus weight, fitting a straight line with one variable and asking what's the slope. And there it is. It's a pretty small number because the weight is measured in like thousands of pounds. So the interpretation here is if you change weight by 1 pound, you reduce highway gas mileage by about 0.0031 miles per gallon. Or said another way, an extra 1,000 pounds of weight is about a 3.1 mile per gallon reduction in gas mileage. That's an overall relationship right there. And if we go fit the multiple regression relationship, we get different answers. Okay, and if we go back to the fitted relationship here for the multiple regression model, before, so what's the partial slope on displacement here? It's 1.35, and this is versus, if we go back to the plot over here, the overall relationship was 2.5 right there. Okay, so let's contrast those, 1.35 versus minus 2.5, minus 1.35 versus minus 2.5. Similarly, if we look at the partial relationship of miles per gallon versus weight in this multiple regression model, here it is. It's 0.00164, and let's compare that versus the overall relationship, which was down here. It was about 0.0031 right here. So that is different, 0.0031, and of course that's negative. So what's going on here? When we estimate the total or overall relationships, we get an overall slope of 2.5 versus a slope of minus 1.35 on displacement in the multiple regression model. That's about half as big. Similarly, the overall relationship between weight and mileage over here has an overall slope of minus 0.0031, and the partial slope is 0.00164 in the multiple regression model. So how can that be? Why do we get different answers for the partial slopes versus the overall slopes? Well, the short answer is that engine weight and the car weight rather and engine displacement are correlated with each other. And that this idea of holding weight constant is crucial in evaluating partial slopes. This picture right here is giving you a sense of what's going on. So to estimate some kind of loose notion of a partial relationship, we've actually split engine displacement here into 3 categories. And the idea here is to approximately hold engine displacement constant by subsetting the data. So in this left-hand panel, you're seeing the blue dots represent engine displacement between 2 and 3 liters right here. In the middle panel, you're seeing engine displacements between 3 and 4.5 liters. Those are the blue dots there. And in the right panel, between 4.5 and 6 liters, the very, very biggest engines, which are probably trucks or very, very big sports cars. And in each panel, the red or pink dots here represent the full data set. Okay? And what I want to get across here is that within each panel, if we look at let's just take the left-hand panel over here. And we look at the blue dots only. These are the cars that have engine displacements between 2 and 3 liters. The slope between weight and highway miles per gallon is that right there, the blue line. Now we look at engine displacements between 3 and 4.5, and there's the slope. That's the blue line. Now we look at engine displacement between 4.5 and 6, and that's the slope, the blue line right there. And you should compare that to the red line, which is, it's the same red dots and the same red line within each of these panels. That's the overall relationship between mileage and weight. And you notice that the partial relationships holding engine displacement constant are much shallower, noticeably shallower than the red line. The blue lines are less steep than the red line. And that's reflecting the fact that as we move up from one category of engine displacement to the other, small engines to medium-sized engines to large engines, Yes, engine displacement is changing, but weight is also changing. You notice that the cars that are in this panel over here tend to be at the left-hand bit of the axis. The cars in this panel tend to be in the middle, and the cars in this panel tend to be over on the right-hand side of the axis. That reflects the fact that engine displacement and weight are correlated. Bigger, heavier cars tend to have bigger, higher displacement engines. And as a result, once we hold engine size constant, we end up with a different estimate of the relationship between weight and highway miles per gallon. So, this is a subtle issue. The idea that multiple regression modeling is implicitly adjusting or holding other variables constant, estimating a partial slope or a partial relationship, is not easy to understand at first blush. I claim that this picture right here is giving you some idea of what's going on, that when you actually go hold things constant, not by running a model, but by simply subsetting the data and assuming that the variables within each subset are relatively constant, you can see that the partial relationship, in particular the blue lines, are different than the overall relationship, the red lines. And it's these blue lines within each panel that are much, much closer to what a multiple regression model is actually estimating as a partial slope.